Good morning. Today we are discussing about power system stability equal area criteria. It is coming under the module 6 and this is the fourth part of our lecture. In the last class we have discussed about the swing equation. Swing equation connecting the mechanical equivalent and the electrical system of a synchronous generator. It is required since whenever there is a sudden or a large variation of load or due to fault, there may be a change in the rotor position with respect to stator axis, and it will create a mechanical change in the rotor angle. Therefore, swing equation is derived, and solution of the swing equation required for the analysis of transient stability. So, equal area criteria is a method which is used for the solution of the swing equation. So, why it is required? It is required for the analysis of the transient stability. So, this is the point we have to remember first. It gives the solution for swing equation for transient stability analysis. And the second point is, it is actually a graphical solution. It is not like a mathematical solution. We are doing some equations, we are calculating some equations and all. It is not coming under this equal area criteria. We are drawing a graph and we are just analyzing that graph, and it is giving some conclusions, and we will be reaching in some conclusions regarding the stability. And it is used for a single machine system. That means one generator is connected to the bus. It is not applied for multi-machine systems. That reason is specified here. Now the fourth point is, it is derived by considering the first swing of the machine. That means a machine starts to oscillate from some position due to some changes in load or fault, and it will make some swinging of the machine or oscillation of the machine. Usually that swing will be maximum during the first swing. If you are considering a pendulum in a clock, if a pendulum is free to oscillate, then that oscillation will be maximum during the first swing. Similarly here also this oscillation or the swing will be maximum during the first swing. Therefore, if it is stable during the first swing, it will be stable in subsequent swings also. Therefore, we are considering the first swing, that means first oscillation with respect to some point, with respect to the equilibrium point. And it cannot be applied for multi-machine system. Why? There are chances of losing the stability in subsequent swings for multi-machine system. If it may be stable during the first swing, it may be the maximum swing also, but there are chances of losing the stability in the other subsequent swings. Therefore, we are not applying it for the multi-machine system. Now, equal area criteria is derived using the swing equation for a machine connected to an infinite bus. Now, the swing equation we know, this is the swing equation, m into d square delta by dt square equal to Pa, accelerating power, which is equal to Ps minus Pe, or which is equal to Ps minus Ev by x into sine delta, that is P, electrical power output. Now, what we are doing, we are multiplying both the sides of the equation by 2 into d delta by dt, and we are integrating with respect to time. So, we are multiplying this equation on both sides with the 2 into d delta by dt. So, what it will become 2m into d square, m into d square delta by dt square already, it was already there. Now 2 into d delta by dt will also come, and we are integrating it with respect to time. So it is also coming, and in the right side again 2 into d delta by dt is integrated with respect to time. Now if we are checking this, we can say this, what the term inside this integral can be written like this: d by dt of m into d delta by dt the whole square. If you are doing this, m is a constant and it will be coming outside. Now we are differentiating this d delta by dt whole square. What will be the answer? 2 into d delta by dt, and this d delta by dt is differentiated again. This, it will be d square delta by dt square. So 2m into d square delta by dt square into d delta by dt dt. So here there is an integration and a differentiation. If both are coming together, it will cancel each other. So what we will get? M into d delta by dt the whole square is equal to 2 into integral ps minus pe d delta. Now actually this bracket is coming here, m into d delta by dt the whole square, not here. What is d delta by dt, which is equal to 2 by m integral ps minus pe d delta, root of 2 by m integral ps minus pe d delta. Now so what we are getting now d delta by dt. So we got d delta by dt equal to this term, root of 2 by m into integral ps minus p into d delta. So what is d delta by dt? It is the variation of delta with respect to time. So we are considering the oscillation of the synchronous machine, that is there is a synchronous generator and it is connected to a load, and this load is varying. With the variation of the load, synchronous generator is varied its rotor axis. There may be its rotor is rotated with a speed ns, synchronous speed ns. Now there may be a variation in this. So this is a stator axis, this is rotor axis. It was rotated at ns and this angle is delta. Now this rotor speed may change due to load variation. So this starts to rotate. So delta 0 was the first value, earlier, or at the beginning delta 0 is the initial angle, initial load angle or torque angle. Before any disturbance occurs, at that time there was no variation in delta because it was constant, that delta 0 was constant, and this machine is rotated with a speed ns. At that time there is no variation in delta, and d delta by dt equal to 0. Now when there is a variation happens, load variation happens, and delta starts to change, and at some other point this d delta by dt will be again becoming 0 after the variation. After this variation, we can consider a oscillation of a pendulum. So it is starting from here, there was no variations, and it is oscillating and it is reaching here. So at this point A, it is starting, no oscillation. At the beginning there was no oscillation at that position, and it is oscillating, it is reaching here at B. At the B again there is no oscillation. Similarly, a synchronous machine starts to oscillate from delta 0. At that time d delta by dt equal to 0, and it is oscillated, and after the first swing completed, at the final position again d delta by dt equal to 0. Let it happens at an angle delta. So we consider two positions. First position corresponding to delta 0, where d delta by dt equal to 0. Then the oscillation starts, and at the end of the swing d delta by dt again becoming 0, and it happened at a point delta. Now it will not stop there. It will again, if we are considering a case of pendulum, it will again oscillate. And if oscillations are reducing, and it will finally it will be coming to some point here. Similarly here also, after this delta, oscillations continues, but at that position for an instant that d delta by dt will become 0. So at two positions, d delta by dt equal to 0, d delta by dt at delta 0 equal to 0, d delta by dt at delta equal to 0. So now we are again considering this relation d delta by dt equal to, we got from the derivation like this, and we got some 2 points. So we are considering it as two extreme points. So at these extreme points, its value becoming 0. This we can apply as the limits of the integration. If you are applying that as the limit of the integration, it is mathematically correct that if at those points this d delta by dt will becoming 0. So at these 2 points this is becoming 0 means we can say if these two are 0 means integrating from delta 0 to delta, that is this right side, this right side also we can, if this is 0 means this right side also 0. How we apply these limits here? If in the left side we are applying 2 points at delta 0 and delta means, at the right side if it is 0, we will be giving it as the two limits. So from integral delta 0 to delta, ps minus pe d delta equal to 0, or we can say integral delta 0 to delta pa d delta equal to 0. So this is the point we should remember here. So this derivation they can ask for your exams. That means prove the equal area criteria, prove the conditions of the equal area criteria. So for that question you have to answer like this. You have to start from the swing equation and you have to multiply like this, and you have to derive this relation, and after that you have to specify the 2 points, and you have to specify about the variation of the delta at these 2 points, and applying the limits, applying these points as the limits for our integration. So we'll be getting like this. So what if an integration is 0 means what? From some point to some point, if you are integrating a curve, if it equal to 0 means mathematically what? Practically it means integration means we are finding the area under a curve. So here from delta 0 to delta, its integration is becoming 0 means that area under this PA, accelerating power, is becoming 0. So that is the point you should understand from this. If this integration from delta 0 to delta is 0 means that area we are considering under this accelerating power is becoming 0. So PA d delta is becoming 0. Under this area under the PA is becoming 0. Now what is PA, accelerating power? Earlier we have gone through this. PA is equal to mechanical power, PS minus PE. The difference between PS and PE is known as PA, accelerating power. It was 0 under balanced condition. It was 0. But whenever there is a fault, it is not equal to 0. At the time of fault, PE is reducing. There is no change in PS, and PA is positive. It is an accelerating power. So acceleration happening. So corresponding to that, we will get an accelerating power. If it happened from delta 0, we can say this power is increasing. PE is there is a change in PE, and if PE is less than PS, whenever there is a fault means PE decreasing. So if we are considering this diagram, this straight line is representing PS. This is PS, and that is the mechanical power. It is a constant. This mechanical power is not changing in case of a generator. It is not instantaneously changing in a case of a generator. So always we are providing the same power. At this point both are equal. There is no acceleration. But if we are coming to this side means PE is less than PS. That means there will be an acceleration. So A1 is representing an area which is an accelerating area. Now at some time this PE may be greater than PS. If this term is greater than, if PE is greater than this PS, which is a constant, so it is greater means it will become negative. If this is negative means it is decelerating. So in this area, if you are checking, this is PS, which is a constant, but PE, this is PE. This PE is greater than PS means at that point this PA is becoming negative. So it is representing decelerating power. So what A1 is representing? A1 is representing an accelerating area and A2 is representing a decelerating area with respect to this point. So these things we will be discussing later. At that time it will be more clear, but now you should have to know something, some points you should have to note down here. So with respect to this point, whenever P is less than Ps, at that time this Pa is positive, means it is an acceleration. Whenever P is greater than Ps, at that time it will be negative and it is deceleration. So area corresponding to these two, we can say it is A1 is accelerating and A2 is decelerating. So these are the extreme points we discussed earlier, delta 0. We are starting from here and we are ending here, delta. So in between these two, this whole area is representing the power, total PA. But in that there are two sections are there. One is accelerating and another one is decelerating. So for this stability, we can say these two areas to be equal, to be even. A1 and A2 we are comparing in the stability analysis. For in transient stability analysis, we are comparing these two areas, A1 and A2. Now, these points you have to note here. The area under the PA should be 0. So, how this area? So, from the previous point, we understood that this area should be 0. How an area is becoming 0? Area will become 0 whenever there are positive and negative areas which should cancel each other. So there should be accelerating and decelerating areas, decelerating powers. The area under PA should be 0, which is possible only when PA is both accelerating and decelerating powers. So there should be accelerating and decelerating powers. That means whenever a generator is oscillating, sometimes up to some point it should be, PE should be less than PS, and after crossing some point, PE should be more than PS. So both should happen. Both should happen. Then only this area will become 0. Okay. Now this third point is whenever PS is greater than PE for positive area. If this is for a generator A1 and PE greater than PS for negative area A2. Here A1 is accelerating area and A2 is decelerating area. Now equal area criteria states that for stability, net area covered between two swinging points during the first swing is 0. That is, here the swinging points are corresponding to delta 0 and delta. Between these two, the net area should be equal to, net area covered is equal to 0. Area covered during acceleration is equal to area covered during deceleration. So this is the statement for equal area criteria. Now we can expand this statement like this. This A1 equal to A2 is an margin. That means at that point it will become critical. It is the maximum point for stability. That is, it is critically stable. Marginal point for the stability. Marginally stable. Whenever A1 is less than A2, that means accelerating area is less than decelerating area. This machine is stable. Whenever accelerating area is more than decelerating area, this machine is unstable. So these are the conditions for stability. So this is regarding equal area criteria. Equal area criteria is used for the solution of the swing equation. So we are considering the first swing. At that time there should be two areas, accelerating area and decelerating area. If both are equal means it will become critically stable. That is the maximum limit for the stability of the synchronous machine. So with this I am stopping here. We will be continuing in the next class. Thank you.